Okay, welcome back for the last session of the day. So we'll have one talk in this session given by Professor Diptiman from Indian Institute of Science, Bangalore. And he'll be talking about OTOCs and conservation laws in periodically driven system.
So first of all, I'd like to thank the organizers for inviting me to give this talk. So this is work done with two PhD students, Samudra Sur, who is here in the hall, and Srimoy Aditya. And it's about two different things, each one of them done by one of them. And that's why the title is a bit long, because the title is just the combination of the two different talks. Okay, so the first talk will be about, we have a periodically driven system on an open chain, and there are n modes which appear sometimes, and the effects that those n modes have on the out of time ordered correlators. The second talk will be what happens if you have periodically driven systems where the potential also is periodic in space. And then we find that you can have local conservation laws can appear. Okay, so the outline is as follows. So first I'll tell you about a brief introduction to periodically driven spin half XY model in a transverse field. The idea of out of time ordering correlators, the effects of n modes, and also the effects of reflections from the ends of the system on the OTOCs. So that's the first part of the talk. And then the second part is about periodically driven tight binding fermion models with potentials which are periodic in space as well, and nearest neighbor interactions. I'll say a few words about Floquet perturbation theory and Floquet Hamiltonian. And then this concept of dynamical localization and local conservation laws. And then the interesting things that can happen if you include interactions, if there are resonances which occur for certain special driving parameters, and something called Hilbert space fragmentation. Okay, so the out of time ordered correlator. So if you have two operators, A of, which is a function of time, and B, which is at time t equal to 0, then the OTOC of these two operators is defined as the expectation value of the string of 4 objects, AT, B0, AT, B0. Now this expectation value can be taken in the ground state, that would be 0 temperature, or all states, which is infinite temperature, or at any temperature. So I'll specify which one we consider in our work. And A of t just means the Heisenberg operator. Now in the work that I'll describe, is A and B turn out to be the Pauli operators. And so their square is 1. And in that case, you can show that the infinite temperature expectation value satisfies this relation, which means that this OTOC is always less than or equal to 1. And it's equal to 1 only if this correlator A of t with B of 0 is 0. Okay. Now the point about the OTOC is that it is known that this is sensitive to the spreading of quantum information, unlike the 2-point correlator. And so I'll actually show you a plot where you'll see that the 2-point correlator actually doesn't give you much information about anything. But the 4-point correlator, the OTOC, gives much more information. Okay, so the model we'll consider is the spin half XY model in a transverse field. So this is the form. So X, Y, and Z denote the spin half Pauli operators. And so we have, this is a one-dimensional system, nearest neighbor couplings between X with strength Jx, Y is with strength Jy, and there's a field in the Z direction. Now, it's, as you know, this can be mapped to a model of spinless fermions by doing this Jordan-Wigner transformation. So if you denote the spin down at a site as the state which has no fermions, and the spin up at some site as a state with 1 fermion, then the Jordan-Wigner transformation is as follows. So there's a string of Zs from the site, from the end of the system, site 0 to n-1, and then xn minus yn. That's the raising, spin raising lower, spin raising operator. So that's the annihilation operator. And the spin raising operator is the creation operator. And so these satisfy the usual fermionic anti-commutation relations. Okay, so the spin Hamiltonian turns out to be quadratic in terms of fermions. That's the purpose of the Jordan-Wigner transformation. So it has a part proportional to Jx plus Jy, which is just hopping between neighboring sites. Then there's a part proportional to the difference, Jx minus Jy, which is a superconducting, P-wave superconducting kind of term. And then the magnetic field actually becomes a chemical potential for the fermions. So it turns out this is well known that If H is less than the sum of Jx plus Jy by 2, then the system is in a topological phase and it has a zero energy Majorana mode localized at each end of a system, long system. And in a non-topological phase when H lies outside this range. And there are no n modes in the non-topological phase. The other thing to notice is that the operator Z is purely quadratic in terms of the fermions. So Zn is just I, A, and Bn, where An and Bn are defined as follows. So they're Majorana operators, they're Hermitian operators. Whereas X is a non-local operator in terms of fermions. It consists of the string of Z's, which is the same as I, Aj, Bj, product over J, and then ends with a Bn. So this is going to be very important, the fact that X is non-local and Z is local in terms of fermions. So how do you do the calculation? If you have an OTOC of X's, then that's a little hard to calculate because each X, as I said, is a product of string of A's and B's. And so that involves a product of 4L plus 4 Majorana operators if X is at site L. Whereas if you have a product of Z's, the OTOC of Z involves 8 Majorana operators because each Z is just quadratic in terms of Majorana operators. In any case, these can both be calculated using the Pfaffian method for Wick's theorem. So there's a good discussion in this paper. In fact, this is the paper from which we use many techniques in our calculations. Okay, so first of all, let me just show you the result for the infinite temperature OTOC. This is for the undriven model, okay, before we do any periodic driving. So on the left, we have the Z OTOCs, and on the right, we have the X OTOCs. And the top two figures are when you're in the non-topological phase, when H is large. And the bottom two figures are when you're in topological phase. So first of all, you notice that all the pictures show this kind of light cone structure. Okay, so the quasi-particles in this system, they travel with a certain maximum velocity, the Lieb-Robinson bound, and that gives you these back and forth straight lines. But you also notice that the X OTOCs, which are on the right, which remember corresponds to the operator which is non-local in fermions, that has much more structure. So you see that between two of these straight lines, so start at the bottom, you have a black region here. So here, this X at sites L and 0 commute with each other. And that's why you get a value of 1. But then above this line, it has a value of -1. So here there's anti-commute with each other. And then after one reflection, if you go to the next region, then they again commute with each other. So we have this very peculiar structure that the information somehow seems to be getting scrambled. Okay, so those are the light regions where the OTOC is close to -1, and then unscrambled again when the OTOC is close to 1. Okay, and this happens every time there's a reflection from the end. Now, eventually, of course, this will go away if you go to very large times, but at least for the first few reflections, this is very clear. So this is one of the interesting features, scrambling and unscrambling of information. Here is just, I'm just showing it for the undriven model, but you'll see exactly the same thing happens for the driven model. The other thing you notice is that if you're in the topological phase, which are the lower figures, there is some extra structure at the end, and that's because of the end modes. So in some sense, the modes that are there, they trap some of the quantum information. So what escapes out into the bulk is a little bit less than what you get over here. Okay, so the end modes are also trapping some of the information. Okay. So I've already told you all this. The OTOCs show a maximum speed of information propagation, and this shows scrambling and unscrambling of the information after each reflection. Okay, so I think I've already told you all this. Okay, now here's just one plot to show you what can you understand from a two-point correlator. So this is just a contrast between a two-point correlator and the OTOC. And for the two-point correlator, on the left we have Z, Z and T, Z00, and on the right we have X. So you see there's hardly anything you can see. You can actually see these light cone in very faint lines, but apart from that, you don't see any scrambling or unscrambling effects. So there's a clear distinction between the information you get from two-point correlators and four-point OTOCs. Okay, so now let me tell you about the periodically driven system, which is what we actually studied. So we consider a time-dependent Hamiltonian. So there's just some general formalism which I'm just giving here for people who may not be familiar with this. So we have a time-dependent Hamiltonian which is repeating after a time period capital T. So then you define a Floquet operator, which is a unitary operator which evolves a system through one time period T, time ordered product of this object. Then you can calculate the eigenvalues of the Floquet operator. They're going to be phases because you use a unitary operator, and they're going to be eigenstates. And then you can use this to calculate various correlation functions. The other thing you can do, given the Floquet operator U, is that you can define a Floquet Hamiltonian. So U is e to the minus I HFT. Now there's a problem here that because HF is related to the log of U, it's not single valued. However, if your driving frequency omega is large or the time period is small, then you can actually define HF uniquely. Okay, so now back to the XY model. So the way we are driving it is we drive the transverse field. So we take this coefficient of the Z term as H1 sin omega t. So it's a sinusoidal driving. Then it turns out, depending on the various parameters, there may or may not be localized N modes. But if you have N modes, they can be of many different kinds. Now the Floquet eigenvalues of the N modes may be either +1 or -1, and this is very well known. Many people have noticed that driving can produce Floquet eigenvalues which either have 0 quasi energy or pi quasi energy in some units. But you find that sometimes you also get other localized N modes for which the Floquet eigenvalues are some other phase, not necessarily 1 and -1. And somehow this doesn't seem to have been noticed much in the literature, but I'll show you that these are there in this particular model. And when you have these kinds of N modes, the Floquet eigenvalues, they always come in complex conjugate pairs. So there'll be a pair of them at each end of the system. The first two kinds of N modes with Floquet eigenvalues ±1, they have a topological character. In other words, you can actually define a winding number for the Floquet Hamiltonian, and the winding number is equal to the number of these modes. But the third kind of N modes, which are at some arbitrary phase, they don't have any topological significance. So we call these anomalous N modes. Okay. Now for a periodically driven system, there's really no concept of a ground state. So the simplest thing to do is to compute the OTOC in the infinite temperature ensemble. So you basically calculate the OTOC in all the states and add them up with equal weight. So just the trace of over all the Floquet eigenstates. Of course, you could also consider coupling the system to a thermal bath, and then you could look at the OTOC at some finite temperature, but we've not done that. It's a more complicated calculation. Also, because this is a periodically driven system, it makes sense to calculate the OTOC only at values of t which are at integer multiples of the time period t. So these are the stroboscopic OTOCs that we are considering. Okay, so the OTOCs take this form. So A0, so 0 means the leftmost site of the open chain at time 0, then A at the site L at time nt, where n is an integer. And so this is the Heisenberg operator. So A, L, nt is just u to the minus n, A, L, u, n. Okay, so here's a picture. So I'll show you now a few pictures of what can happen for different values of the driving parameters. So for instance, if your Jx is 1.8, Jy is 0.2, H1 is 1, and omega is 2, you get an N mode at each end of the system, which sits at Floquet eigenvalue equal to +1, or Floquet quasi energy equal to 0. So these are the bulk states. Okay, so they have wave functions which are spread all over the bulk, and these are states whose wave functions are localized near the two ends. So the Z OTOC gives you this light cone structure, which is very faint, and the X OTOC gives this structure. So it really resembles what you got in the time independent problem. However, you do notice that at the left end, which is, so you're launching this OTOC from the left, and you do see that there is some signature of the N modes at the left end of the system. So you see this line here. So this OTOC basically tells you that there are N modes. It's a way of detecting that there are N modes in the system. Okay, so here are two other cases. So here's a case where you have both 0 quasi energy N mode, and you have these anomalous N modes. And as I said, they always come in complex conjugate pairs. So this is the Floquet eigenvalue in the unit circle e to the I theta. And this time you discover that, so for this case again, you find that you have an effect of these N modes on the left end. But there's not much difference between the Z OTOCs and the X OTOCs here. Okay, so basically the N modes trap all the information there and nothing escapes out into the bulk. The third picture is where you only have anomalous N modes, and there are actually two of them at each end. This separated by a small amount, and you find that there are oscillations in the OTOC as a function of time at the left end. So it turns out that this oscillation frequency is inversely proportional to the energy difference, Floquet quasi-energy difference between these two modes. Okay, so I'm just plotting the eigenvalue of the Floquet operator U. So it's e to the I theta. So this is just cos theta. So it's just cos theta and sin theta. So basically, it's all the points in the unit circle are the eigenvalues. Okay, so as I said, you see oscillations at the end, whose period is inversely proportional to the gap between the quasi-energies. The other thing to note is that there are also, as I said, when there are N modes, they're at both ends of the system. Okay, and if the system is very long, then of course they're not degenerate, they don't hybridize with each other. But if the system is not infinitely long, then of course they'll hybridize with each other. However, if the system is quite long, like 40 sites, the hybridization is very small. So hybridization actually falls off exponentially with the system size. It goes as e to the power minus L divided by the decay length. And so here's a system where the zero quasi-energy N modes have a gap between them of 10 to the minus 11, whereas the anomalous N modes have a gap between them 10 to the minus 9. So if you look at this OTOCs at very long times, you see that there are these oscillations which appear after the inverse of this gap. So 10 to the power 9 and 10 to the power 11. Okay, so that's just to show you that you do see oscillation periods proportional to the energy difference between any pair of N modes. So whether they're short, whether they're small oscillation period, if the difference between the quasi-energies is large, or very long periods if the difference between the quasi-energies are very small. The final thing is that we looked at this speed, that light cone, those straight lines, the slope of those, as a function of various parameters. And so here's a plot of that as functions of these different quantities, as a function of the driving frequency omega and the driving amplitude h1. And so here's a plot of the V max as a function of omega for different values of h1. So the limits of large omega, which is the fast driving, where you can actually use something like the Magnus expansion, and the limit of very small omega, where it's almost an adiabatic driving. So in those two limits, we can actually calculate this speed analytically, and it matches. So these dashed lines give you those analytical results for large frequency and small frequency. But at intermediate frequency, you get a very complicated pattern of driving frequencies with lots of oscillations and so on. And of course, this is very hard to understand these analytically. Okay, so that's the first part of the talk. So to summarize, for finite system, I've shown you that OTOCs provide a method for detecting modes localized at the ends. Only the anomalous modes produce oscillations in the OTOCs, while the modes at the zero quasi-energy trap the quantum information at the ends. And both of these we can understand analytically in terms of wave functions of the N modes in the fermionic language. At the end of the talk, I'll give you the references for this work. For operators which are non-local in terms of fermions, the X-spin operators, the OTOCs also show a scrambling and unscrambling of the information after reflection. And this is something that we don't really understand analytically. We are working on this, but so basically it's this picture. Okay, so even this picture, that the fact that this value of the OTOC keeps alternating between two possible values as you go up. So you sit at a particular lattice side, but you go up in time. You see this alternating pattern. So this is something that we really don't understand analytically. Of course, at very long times, everything gets washed out and you get a uniform color. So this is only something that you see for the first few reflections. The other thing to notice is that you don't see this pattern if you have periodic boundary conditions instead of open boundary conditions. So they have something to do with reflections from the ends. Okay, you don't see them at all if you just use a periodic boundary condition. So they're not just some kind of recurrence or that you see in many other quantities. So there's something special about reflection from the ends of an open system. Okay, so that's one of the things that we need to understand analytically in this problem. Okay, so let me pause here. Are there any questions about this part of the? Okay, so if not, let me get on to the second part. So this is the part where I'll tell you about what happens when we take a model of interacting spinless fermions. So this is your tight binding part, nearest neighbor hopping. Then there's a part which has to do with periodic potential. So we studied two periods, period 2 and period 4. And the strength of this is being driven in time periodically. And we have taken a square pulse form for the driving. Okay, so you have one value of mu for half the time period and the opposite value for the other half of the time period. And then we also have an interaction, nearest neighbor interaction. These are spinless fermions. Okay, so first of all, it turns out that if this strength of the driving mu and the frequency of the driving omega, these are much bigger than the hopping amplitude and the strength of the interaction, you can do a perturbative calculation. Okay, so let me briefly describe this kind of Floquet perturbation theory. So given a periodically varying Hamiltonian of this form, there's a time dependent part and there's a time independent part. So the perturbation theory goes like this. So you have an eigenstates of the time dependent part. So this is a little bit different from the usual time dependent perturbation theory, where you take the time independent part with the H0 and the time dependent part as the perturbation. This is the opposite. So the eigenstates of H0 defined as psi n. So it's very important. This thing only works if the eigenstates are time independent, but the eigenvalues, instantaneous eigenvalues, of course, change with time. And so to find the Floquet eigenstate, which lies close to this when you turn on the perturbation V, you assume that a Floquet eigenstate is a superposition of all these eigenstates of H0. And then you do the usual thing for perturbation theory. You assume that one of them is close to 1 and the others of order V, and then find solution of the Schrodinger equation. And most importantly, impose the Floquet condition that the psi at after one time period capital T should be some phase times psi of 0. So when you impose that, you discover that the coefficients, so one of the coefficients is close to 1. The other coefficients, which are of order V, have this kind of an expression. Okay. So if you look at this expression, you find that if the numerator of this is 0, then that means this coefficient is 0. And if this is true for all values of m, that means the system just stays in one of the states that you started with, and it doesn't go to any of one of the other states. So basically, the driving has no effect to first order and V, and the Floquet eigenstate remains frozen in one of the eigenstates of H0. So that's one extreme limit, that's freezing. The opposite limit is when the denominator vanishes. Then, of course, this perturbation theory breaks down because the very first deviation from the initial state is diverging, and then we have to do degenerate perturbation theory. Okay, so if there's a subset of states for which this is 1, so that's when this denominator vanishes. Then you have to do degenerate perturbation theory, and you discover the Floquet Hamiltonian has matrix elements given by this. Okay, so there's a review of this which you can look at, written by 3 people who are all in this hall. So the Floquet Hamiltonian, so first I'll tell you about the period 2 model. So this potential is alternating, right? So it's a staggered potential, and its strength is varying as a square pulse, as I said. How much time do I have actually? Oh, plenty of time. Yeah, okay. So now because this is period 2, the simplest thing to do is to define unit cells. So if the total system size is L, there are L by 2 unit cells, and each unit cell has a site A on the left and site B on the right. And then again, you assume J and V, the interaction and the hopping are much smaller than mu and omega. So you discover the first order Floquet Hamiltonian has this form. To this order, first order, the interaction doesn't change at all, but the hopping gets normalized like this, where this parameter A is pi mu by omega. So it's clear from this that if mu by omega is an integer, this term vanishes and we get dynamical localization. Okay, so the hopping entirely disappears. This is similar to what you saw in, there was an earlier talk today where if you drive sinusoidally, then the condition for vanishing is the J0 being 0, the first Bessel function 0. For square pulse, it's this condition. Okay. So if this hopping term vanishes, then you're only left with the second term. So it's a really simple Floquet Hamiltonian. It's just got this interaction piece. So this gives rise to an extremely simple spectrum of Floquet quasi-energies. And so you get a number of many body flat bands with discrete values of EF. And we have also looked at the entanglement entropy between two halves of the system and called the half chain entanglement. So here's a picture which shows you both of these things. So here are the Floquet quasi-energies as a function of the different states, increasing order of the quasi-energies. That's on the left, and the right shows you a plot of the half chain entanglement versus the Floquet quasi-energies. So first of all, if you are exactly at a dynamical localization point, so mu is equal to omega. So remember that the dynamical localization condition is that mu by omega should be an integer. So there you get these flat bands, and therefore in this S versus E plot, you have these vertical lines. Okay. Whereas if you're slightly off a dynamical localization point, mu is 20 but omega is 22, then of course the bands are no longer completely flat, and all these finger-like things get broadened out. The other thing you can look at is something called the Loschmidt echo. So you start with some initial state psi, which I noticed that I forgot to put down here, what the initial state psi was for this particular picture. You evolve it for n time periods and then look at its overlap with the initial state. So that's a Loschmidt echo. And you find that if you are exactly at a dynamic localization point, mu is equal to omega, then it oscillates for a very long time. Okay. So basically, you have almost perfect recurrence. Eventually, of course, this will go to some constant, the oscillations will die away. But it takes a very long time. This is the number of time periods on the x-axis. Whereas if you're away from a dynamical localization point, mu 20 and omega 22, then it drops very fast to some value. Okay, now let me tell you about the period 4 model because it's more interesting. So consider a non-interacting system, first of all, V is 0, and the potential has this period 4. So when you do this first order Floquet Hamiltonian, then you discover that as a result of renormalization because of the driving, the hoppings between neighboring sites, they develop this period 2 structure. So the hopping between 4j plus 1 is 1, the next one is m1, then it's 1, then m1 star. So basically, the periodicity of the system reduces from 4 to 2. Furthermore, if your m has this form, so once again, if mu by omega is an integer, alternate hoppings vanish. Okay? So this is actually an extreme limit of the SSH model, where alternating hoppings are 0 and the other hoppings are, let's say, 1, j. Okay, so then depending on, if you take an open chain, then depending on whether the last bond is has strength 0 or strength non-zero, you'll get an N mode. Okay, it'll be in a topological phase or non-topological phase. So here's a picture of that. So this whole thing depends on this phase phi that you put in this periodic potential. So by changing phi, you can actually go between a topological phase or a non-topological phase. Okay, now it's clear that for the same system, if you have hoppings which are alternately 0 and 1, then the system basically breaks up into pairs of nearest neighbor sites, which are decoupled from all the other pairs. Okay, so let's denote this pair of sites as a unit cell J, consisting of these sites A and B. So the number of fermions in the unit cell J, so Na plus Nb, is a conserved quantity for all values of J. And so you see, you have a L by 2 of these conserved quantities, one for each unit cell. So these are the local conserved quantities that appear. Okay, so now we add an interaction. And so for when V is much less than mu and omega, we find that this is the effective Hamiltonian. Okay, so this is, so you get a hopping only within a unit cell between A and B. And then you have an interaction, but the interaction is of course within the unit cell as well as between two unit cells. Now in each unit cell, the total fermion number can take values 0, 1 or 2. Okay. So if the if the fermion number is 0 or 2, then nothing can happen in that unit cell because of this hopping. Okay. So that unit cell, we call it an inert unit cell because there's no dynamic associated with that unit cell. But if the fermion number is in a unit cell is 1, then you can either have a state which is 1, 0 at A and B or 0, 1 at A and B. 5 plus 5. Okay, thank you. So there are two possible states if the fermion number in a unit cell is 1, 1, 0 and 0, 1. So we map these two to the states of a spin half object and call that Z equal to +1 and -1. Okay, so then this hopping term A dagger B plus B dagger A is a spin flip operator, right? Because it takes you from 1, 0 to 0, 1, or vice versa. Okay, then you can work out what, so we know the first term, the hopping term is just this, the X spin flip operator in that unit cell. And this interaction V, you find that it has this form. So it is takes the form of a coupling between the Z at the unit cell J with Z at unit cell J plus 1. So if you just look at this part, it's just the transverse field Ising model. Okay. So somehow this period 4 model sitting at a dynamical localization point with interactions has somehow become this transverse field Ising model. Now an extra twist to this is that you also get a extra field term at the two endpoints of the system. And it looks like if you include these, then it's a little hard to solve because these Zs are non-local fields in terms of Jordan-Wigner fermions. However, it turns out that I'm actually rushing here. Sorry about that. So you have a series of L/2 unit cells bounded on the left and right by inert unit cells, and where you have these boundary terms, boundary magnetic fields. But it turns out that even this can be solved analytically. So what you do is that you introduce 2 extra sites at the ends, and then you couple them to these 2 sites, Z2 and ZL/2 minus 1. So you basically just extended the system by 2 sites. When you do that, you get just the transverse field Ising model without any extra boundary terms. But the boundary fields, depending on the boundary fields, you can have 4 sectors, +1, -1, etc. And those are exactly the 4 terms that you can have here, depending on whether the inert cells on the 2 sides have fermion occupation number 0 or 2. Okay, so again, here's a picture of the half chain entanglement. So one of the things that I'm showing you here is that this on the left is the result from exact numerics. So we actually calculate this time ordered product of e to the minus IHT, find the Floquet operator U, find the eigenstates and all that. So that's the picture on the left. The picture on the right is just from this first order perturbation theory. And you can see they agree pretty well. And that's really because the conditions for Floquet perturbation theory are very well met here. Mu and omega are much bigger than J and V. Now the quasi energies match quite well between the 2 pictures, but the first order Floquet perturbation theory consistently gives a much smaller value of the entanglement entropy compared to the exact numerics. And that is understandable because in Floquet perturbation theory, you have this approximate local conservation laws. So the Floquet perturbation theory is actually giving a much simpler picture compared to what you really have. It's the higher order terms will actually tell you that these local conservation laws are broken by small terms. Okay, so that's the reason why the half chain entanglement doesn't match so well. Basically, what I'm saying is that the energies match well, but the wave functions don't match well between exact numerics and first order Floquet perturbation theory. So this is a similar picture. So this is for so this is just to show you that there are a few states which are very low entanglement entropy, very close to 0. And these come from patterns of fermion numbers like this. So you can see, for example, for this state where the fermion numbers are 2, 2, 2, 0, 0, 0. So this is a half filled state, 16 sites with 8 unit cells. So if you cut this in the middle here, then it looks like a product state. So this is a state with very low entanglement entropy. if you also include resonances, so resonances occur when both mu by omega is an integer as well as v by omega is an integer. So all this while I was telling you about what happens when v is much smaller than omega, but now we are allowing the interaction strength to be also of the order of omega. So if both of these are integers, then it turns out you have resonances, states with two particles next to each other have the same energy as two particles not next to each other, because v and omega are integer related. So then it turns out that there are no local conservation laws. The first order Floquet perturbation theory is of course not valid anymore, but you get a form of the Hilbert space which is very interesting. So the old first order Floquet perturbation theory is not correct, but you have to modify it to include large values of v. But you get this kind of a Floquet Hamiltonian, and you discover that this gives rise to something called fragmentation of the Hilbert space. So if you stare at this, you discover that certain kinds of hopping between nearest neighbor sites are not allowed. So if you have nearest neighbor sites 1, 2, then depending on what the occupation numbers are at sites 0 and 3, you may or may not allow hopping between sites 1 and 2. And so because of these constraints, the Hilbert space breaks up into fragments, and the fragments can have different sizes. Here's a particularly simple fragment, 16 sites. If you take this state 1, 1, 0, 0, 1, 1, 0, 0, there's the occupation numbers, you find that there's no matrix element between this state and any other state, according to this first order Floquet perturbation. Okay, so if you start with that state that I just told you about and study the Lock-Schmidt echo, you find that it keeps oscillating for a very long time. And not only that, it always stays very close to 1. So it hardly deviates from 1. Also, it has an appreciable overlap with only a small number of Floquet eigenstates, which have very low half-chain entanglement. Okay, so let me summarize this part of the talk. So what I've shown you is that periodic driving of systems with spatially periodic potentials can give rise to local conservation laws for the first order Floquet Hamiltonian for certain special values of the driving parameters. So this leads to Floquet Hamiltonians which describe the SSH model. And if you include interactions, it can also give you the transverse field Ising model. Then if you also include interactions and resonances along with dynamical localization, then you can get this Hilbert space fragmentation. So here's an open problem. So of course, we know that local conservation laws or Hilbert space fragmentation lead to a lack of thermalization for a long time. Eventually, of course, you'll get thermalization because higher order terms in perturbation theory will kick in. But this is something that we have to really understand properly. What is the time scale beyond which the system thermalizes? Can we understand this analytically? So that's really all I wanted to say. So let me end with the references. So the first talk about OTOCs, work done with Samudra, this is the reference. And the second talk about the local conservation laws done with Srimoy, this is the reference. And here's the funding acknowledgement. Thank you.
Thanks. Diptiman, regarding this open problem, I mean, this thermalization time,
right?
This, wouldn't you expect something like exponential in drive amplitude or frequency? Because this is, I mean, in some sense, I can think of it to be some kind of Magnus expansion in a rotated frame. And then we know that for those kind of expansion, it's exponential in omega. But here you can trade in between V and omega because they have a relation. So I think that would
possibly,
be, yeah.
We have really not studied this,
okay.
But because it's an interacting system, a little more complicated than otherwise.
No,
right?
This should hold irrespective of.
It should always be exponentially in omega.
At least for this kind of drives, I think it will be. I might be mistaken. I mean, but at least studying those chains for another different systems. I mean, we saw this numerically, and you know.
Okay.
Okay.
Yeah, you may be right. We've just not studied this.
Other questions? Okay, maybe I ask a question. Okay. So when you have this higher order term, so generally you write some, so you have some approximate conservation, I mean conservation law which will be gone at long term.
So they'll be broken by
so you have to write some description in terms of that, or I mean, like for I think non-interacting fermions and then putting interactions, people write this kind of
Right.
Hmm.
So higher orders, for example, so one of the local conservation laws was that in every unit cell, the fermion number is conserved. So when you go to the next order, you'll get some hopping between one unit cell and the next. So you can write it in terms of intercell hopping, which will break the conservation law. Right. Was that the question?
I mean, can you use this local conserved quantities to write some time evolution, basically, when you have the other terms?
Right. So you'll start with the local conservation law, and then you'll have hopping between unit cells, but that will break this conservation law.
Yeah.
Yeah. So I guess you can't really use the local conservation
Okay.
law anymore.
Any other questions? Okay. If not, let's thank Diptiman.
Okay.